My name is Alinda Kriener, and today we're going to be going over Lab number 1 regarding constant velocity. In this lab, the motion of a kickball being rolled across the table is measured in terms of position on the x-axis, the table, and time in seconds. This position versus time data collected is then compared against a model position versus time graph generated via programming. Let's take a look at the motion of the ball. Now you may be wondering, where's the physics in rolling a ball across the table? Well, you may or may not have heard of Newton's second law, which relates acceleration of an object to its net force. You may be familiar with the equation force equals mass times acceleration. This can be rewritten, as acceleration is really change in velocity, to form the velocity update equation, which states that an object's final velocity is equal to its initial velocity plus the quotient of net force and mass times the time interval of observation. When a force is constant, we can use the final velocity we get from the velocity update equation and plug it in as the average velocity into the position update equation to predict the future motion of an object. This process can be repeated over and over and is much more efficiently done by a computer. Now for this lab, we are hoping to observe constant velocity, which would imply the net force on the moving object is zero, which as you can see would simplify the velocity update equation to the final and initial velocities being the same, thus constant velocity. After recording the motion of the kickball across the table, I used Tracker to analyze its motion. First I had to specify what frames of the video I was going to observe the motion in. I used frames 101 to 150, as I didn't want to include the initial acceleration from rest of the ball. After specifying my frames, I calibrated the diameter of the ball, positioned the coordinate axes, and calibrated the center of mass of the ball in each frame. After that, I calculated the initial velocity of the ball using the first two time and position readings, and marked down the final and initial times and initial position. My kickball's motion results came out to be very linear, as you can see in the tracker graph that graphed the kickball's position and time. Next, it was time to make the constant velocity model in GlowScript. In order for the code to properly correlate the kickball's model motion to Newton's second law, I needed to sub in values for the ball's mass, radius, and initial position and velocity calculated via the tracker data. Additionally, in order to model constant velocity as we discussed earlier, the net force on the kickball has to be entered as a zero vector. The equations for velocity and position also need to be updated to properly represent the velocity and position update equations so the computer could effectively predict the ball's motion. As you can imagine, the model's results were perfectly linear. So now let's compare our actual results with the model. Here's the experiment versus model graph that graphs our observed position and model position versus time. While the experiment line is fairly linear, there are still some discrepancies from perfect linearity. Why is that? First of all, you might have noticed that we have a negative sloping line on the graph. That is because I established the coordinate axis in tracker with the ball's initial center of mass as the origin, and the left direction correlating to the negative x direction. You may also see this gap in between the model and the observation position lines. This gap can be attributed to the fact that our kickball didn't travel in a perfectly straight line. In fact, if we look at the video again, it veered off to the right of the table towards the end of the frames. Furthermore, the slope of the observation line is less linear, meaning the velocity isn't perfectly constant, inferring that there isn't actually a net force of zero. Other contributing forces, such as friction from the table, though they may be minor, impact the motion of the ball. In conclusion, we compared the motion of a kickball being rolled across the table with the model of a perfectly constant velocity in order to observe the kickball's motion. We used Newton's second law by applying velocity and position update formulas, and we analyzed the real-life contributing factors that can deter an object from perfect constant velocity. Thank you for watching.